So today I'm going to talk about queuing system, actually basics of queuing system. As I mentioned before, this queuing system is main application area of continuous time Markov chain or some stochastic process concepts, okay? And especially in industrial engineering, when you try to design or analyze manufacturing system, service systems, or supply chain management systems, okay? If the system includes any uncertainty, okay, then we usually consider this concept called queuing theory. So do you have any experience about this case? So many people in the line, right? Have you ever visited Everend? T Express, do you know T Express? Okay, to ride such thing, such roller coaster, you need to wait like two hours, right? 2 hours. How about this? New Year's Day, before, after, right? In the high Apple Store. Just before we meet a new device like iPhone 7. Okay, someone tried to wait like a day. And the manufacturing system. If you see the goal, okay, this manufacturing system is like a network of queuing systems. So sometimes we can observe some bottleneck inside the system, okay, a certain step of the process, okay. All the things can be described by some mathematical techniques called queuing theory. Queuing theory is actually based on stochastic process, what we learned just before this class. So queuing model. A simple queuing model includes three components. First, entity arriving to the system. For the service system, it can be customer. Okay, if you consider market, E-mart, Hi-mart. Okay, then this entity can be a customer who try to buy something in the market. Right? If you consider hospital, okay, this population can be patients, okay, patients. If you consider manufacturing systems, this population might be parts, okay, parts, materials, okay, materials arrives to the system, and then machine and worker handles such materials and parts, and then we can get the product. Okay. Second part is servers. Okay. If a customer arrives to the system, then someone or machine, something, can handle this entity to give some service, right? If you consider a dental clinic, okay, then you can see the dentist, okay, and then we have some reason why we need to see the dentist, like some toothache, okay, or you need to get some different services from dentist. And the third and the most important part is this one, waiting line. Okay. So if you can forecast customer arrives exactly, or if you can evaluate service time exactly, no variation, then there is no problem. You can exactly handle the system, control the system, okay? Control the system. The thing is, these arrival times varies, like different from different of for each patients or customers. Okay, parts similar. Okay, in the manufacturing system, even though these parts arriving to the system like within a day, but there can happen, something can happen, right? Something can happen. It can be delayed, or and so on. Many other different. We cannot exactly expect all the things, right? So we need to consider such events in the uncertainty. Okay, uncertainty. Okay, we can model it. So based on the variation of the arrival times and the service times, okay, this waiting line, there exists a waiting line. Okay, if a waiting line is too long, then what happens? If you visit the dental clinic, then there are so many people. You heard that you need to wait like 3 hours. Then what can you do? You can visit another, okay, dental clinic, right? Or you need to wait like 3 or 4 hours. Okay, you need to spend time. Okay, these concepts are very important when you design service system or when you operate the system. Okay, then let's assume that you are a manager. Okay, manager of the hospital. Okay, then you need to determine how many doctors we need, okay, to handle the patients. What do you think? In a patient point of view, if we can prepare as many doctors as possible, then patients feels good. No wait, no waiting line. Okay, as you can get your service instantly, immediately. Good, right? Customer satisfaction goes up, right? But what is the problem? High cost. Okay, this is manager's point of view. When you try to operate the system, then if you hire many doctors, then you need to spend much money for sustaining such a case, right? Okay, we need to think about that. So there are many examples of queuing system. There are actually part of the examples, many things. You can think about service systems with some customers like shoppers, okay, in the market, and then in the checkout counter we have clerks, okay. They are working on calculating how much you need to pay, right? And then sometimes you need to wait like long time, 30 minutes. Sometimes you don't have to wait, right? We don't know, right? But this someone who want to operate the system, they need to evaluate or estimate, analyze the system, okay? Because if you hire more clerks, then you have some chance to earn more money. But we don't know. This event is like usual event or not, right? We are going to consider this based on some probability things, stochastic process. Patients, doctor, waiting room in the hospital as customer, servers, and queue respectively, and so on. You can think about many different things. We can come up with many different kind of queuing systems, but this the system described in the top is the most basic one. Single server, single stage. Okay, one line and one server. Okay, So for example, ATM machine in front of the convenience store, okay, GS 24 or 25, I don't know, and so on. Anyway, ATM machine, one line, one machine, right? And then how about the second case? In the cafeteria, you need to wait in the one line. You can get entree, appetizer, and then soup, and then you need to pay. Okay. Between the process, there is no waiting line. How about this case? Single server queue in series, like in the hospital, university hospital. Okay. You need to like if you want to see a doctor, then first you need to check in. Okay. And then in front of the doctor's office, you need to wait also. Okay. How about this case? What do you think? Is there any example? Airport security check system. Okay, in the one line. Okay, and then someone check if this ticket and your ID are matched or not, and then you can consider multiple lines to check your belongs. Okay, and then last one, bank, one line but multiple servers. Okay, and many other different cases you can think about. Very many things. Okay, here is what happened with we can see what happened in the single server single queue. Okay, simple queuing model. So from now we are going to think about simple queuing model like single server single queue. Okay, so we can observe the system behaviors of the system in front of the let's say ATM machine. Okay, from 8 a.m. Okay, 8 a.m. 8:02. Okay, 2 minutes after, a customer arrived to the system. There is no one, so he or she can use the machine immediately, right? And this A will leave 8:05, 5 minutes, 3 minutes after from he arrives to the system. Okay, but the thing is, 8:03 a.m. B arrives to the system, and he or she can observe that someone is using the machine, right? And as long as A is using the machine, B need to wait, right? C arrives to the system at 8:04, 1 minute after. Still, A is working on the machine, B is waiting for, and C need to wait after B, based on first in, first out concept. Okay. And then at 5, A leaves the system, and now B can use the machine. Okay, and so on. So as I said before, the thing is, so how many servers do we need? Okay, to operate the system. Okay, if you install many ATM machines, then we need to pay more and more. Okay, to install and manage the systems. Okay, and if we have small number of servers, machines, then we can expect, maybe we can expect long waiting time. Customer satisfaction gets lower and lower. Okay, so this part, cost for waiting. This one represent cost based on customer satisfaction. Okay, if waiting line is long and long and long, you can lose the customers. Okay, how about this? Cost due to increase of servers like dentist in the dental clinic. Okay, if you hire more doctors, then you need to pay more. Okay, so when you try to design the system, okay, design the system, you need to think about some trade-off relationship between two points of views, like customer's point of view and manager's point of view. Okay, and then you can select the best design parameter, like how many doctor we need to hire, how many machines do we need to install, okay, something like that. Okay, that is the question in our case. Size of the waiting room. Okay, buffer size. Okay, if you rent, okay, the space, then we need to estimate, okay, the size of the space, like dental clinic. Okay, so we are considering such performance measures like utilization of servers, how busy server is. Okay, this is about how busy server is, how busy. Okay, we are going to estimate this utilization as a number between 0 and 1. 1 means 100%. Okay, so if you visit your business, then server working every time, no rest time. Okay, just working means utilization is 1. 0 means no working, just no customer, no working, so utilization is 0. Okay, average waiting time in the queue. If you are a customer, you want to estimate how long do we need to wait in the hospital, right? So average waiting time. Average staying time means waiting time plus service time. Okay, number of customer in the queue or number of customer in the system. Based on such measures, you can estimate how many customer you can handle within a unit time. It is directly related to how much you can earn the money from the customer or parts. Okay, so average profit or cost per unit time we discussed in different examples, right? New spender or SSC inventory policy problem, similar cases, and probabilities. We can examine a certain event. Okay, certain event. The probability of occurring a certain event. Okay, sometimes we want to calculate it. Okay, for example, in the call center problem, you want to check whether you can directly connect to the server or not. Okay, at once. This is very important for the customers. So we are going to formulate this system to analyze, to evaluate such measure, okay, with a certain mathematical notation. Say A of t is number of arrivals until time t to the system. Okay, D of t represent number of departures until time t. Okay, L of t number of customers in the system at t, point of time t, and LQ of t number of customers in the queue at time t. Okay, this is the notation to evaluate the system. Then if you try to draw a graph based on the such measure A of t, D of t, okay, you can imagine the system, ATM machine, okay, like 802, someone arrives to system, right? Then this A of t increased by 1 at that time, 802, like AM. And then we can keep track of the number of arrivals. Then this A of t increases as time goes on, right? And here is the question. What if this inter-arrival time follows exponential distribution, IID exponential distribution? Then what can you say about A of t? This is kind of count process, right? From time 0, as time goes on, we can count number of customers who arrives to the system, right? Then we can say that A of t is, so inter-arrival times are exponential distribution, IID exponential distribution. Then this process is what process? Poisson process, right? Poisson process. In other words, this arrival process is a kind of Poisson process, homogeneous Poisson process. Then inter-arrival times follows IID exponential distribution. Okay. Departures. We don't know what happened in the system. We don't know, but we can count number of departures. Okay. In front of the exit. What? Departure, leave the system. Leave the system. Departure, leave the system. Number of departures. Okay. So we don't know what happened in the system, but we can count number of customers who got his or her service. Okay. Done with the service and then leave the system. Then we can think about that. Okay. For example, in the ATM machine case, 805. At 805, this person A leave the system, right? So 805, okay, departure D of t increased by 1, okay, and so on. Then number of customer in the system, L of t. L of t can be described by A of t minus D of t. We don't know what happened with such customers, such amount of customers like A of t minus B of t. They are in the system. Someone need to wait. Someone getting his or her services, right? We don't know. But this amount of customers should be in the system, right? We can approach this concept. Firstly, we can approach this concept with finite time. Okay, in this, when we consider the system, when you operate the system in finite time, right? Like instantly, event market, something like that. Okay, just 2 days. Okay, something like that. Then we can think about such performance measure based on the data. Okay, data. So A represents first customer entered this empty system. We are going to start with the empty state, and then B return to the empty state. Then WIP from A to B represent average number of customers in the system per unit time from A to B. Okay, we can examine just time period A to B. Okay, and then we can calculate average waiting number of customers in the system. CT, average time, like CT is abbreviation of cycle time. Okay, CT from A to B represent average time spent in the system per customer from time A to B. Okay. Then we can evaluate this WIP, average number of customer in the system per unit time, as 1 over b minus a integral t is from a to b L of t dt. Okay, we can integral L of t regarding time t from a to b, and then divided by a b minus a, total amount of time we observe the system. Then we can get average number of customer in a unit time. Okay, we call this WIP. And then CT can be calculated by, we can consider total amount of W A to B, A to B. We can consider total amount of customers who get the service from time A to time B. Let's say M. A to B. And then we can think about all the cycle times for each customer, large M. Let's say TID represent ith time, departure time for the ith customer. TIA represent arrival time for ith customer. Then this one is average cycle time for the system from time A to time B. And then throughput, average number of customer arriving to the system per unit time, or departing. This is very important measure how efficient this system is. Okay, measure how efficient how efficient and effective this system is. Okay. So later we are going to talk about Little's law, very important formula in IE. But before we consider Little's law, based on finite time, we can also calculate this such throughput using similar concept. So M of this WIP is actually M over B minus A times CTA from A to B, and this M of B minus A, number of customer, M represent number of customer who got his or her services from A to B, and B minus A is total amount of time. Okay, then unit amount of time, how many customer get his or her services. Okay. Okay, so we can think about an example, ATM case. So Donggi asked about this one, why this equal sign is correct, right? So we can think about this case, okay? This graph, okay? We can interpret such a graph, left bottom part, okay, with two different point of views. First one is this, okay. This we want to integrate this, right, and then divided by amount of number of customer who got his or services from A to B. Okay, so this one can be calculated by, for each customer's point of view, departure time minus arriving time times 1, right? Just one customer. Okay, this area is the same as from here, this area and this area, this area, this area. Total area of this marked by light blue can be calculated by this, right? And based on the graph, we can see that this integration is the same as area of this light blue. Because we consider single server queue, very basic queuing system, this one happened. Okay, you can interpret this one two different ways. Because we consider one by one customers by one. Okay, when we consider summation of this departure time minus arrival time for each customer is the same as this area of light blue pulse. And then area of light blue pulse can be rewritten by this, okay, integral a from a to b, a of t minus d of